Ever wondered how the devices we rely on every day, from smartphones to smart appliances, work their magic? It all starts with a tiny but mighty hero, the microchip. In this video, we'll embark on a fascinating journey deep into the heart of technology. We'll disclose closely guarded secrets of chip manufacturing, demystifying the complex process that gives life to these silicone marvels. So, buckle up, because we're about to explore the incredible world of chip manufacturing. How are microchips made? Imagine a world where the power of technology rests in the palm of your hand. That world is our reality, and at its core are computer chips. These tiny marvels, also known as integrated circuits, are the fundamental building blocks of almost every electronic device, with computers at the forefront. They're like the wizards behind the curtain, orchestrating the magic of modern technology. Computer chips are crafted from semiconductors, materials with the remarkable ability to control the flow of electric current. Within their minuscule dimensions lie countless components, including transistors, all working together to process and transmit data. They may be small, but their impact is enormous. These chips emerged as technological heroes in the later part of the 20th century. Their compact size, extraordinary efficiency, and ease of manufacturing catapulted them to stardom in the world of electronics. Now, let's peel back the layers and explore the fascinating world of computer chips, from their fundamental classifications to the magic they weave within our devices. When it comes to crafting the brains of our electronic devices, silicone reigns supreme. This remarkable element, abundant in nature, takes center stage in the fabrication of computer chips. Why silicone, you ask? Well, it happens to be a naturally occurring semiconductor, and that's where the magic begins. Silicon's electrical properties can be finely tuned by introducing controlled imperfections, a process known as doping. This makes it the ideal candidate for creating the tiny switches we call transistors. These transistors are the heart and soul of computer chips, responsible for processing and transmitting data at lightning speed. Transistors are built upon P and N conductive layers, embedded in a doped silicone wafer. These minuscule control units hold the key to manipulating electric voltages and currents, making them the driving force behind electronic circuits. In fact, transistors are the most vital components in this intricate world. Each transistor within a chip consists of P and N conductive layers, both made of silicon crystals. Additionally, there's a layer of silicon oxide, acting as an insulator. On top of this, an electrically conductive layer called polysilicon is applied. The transistor has 3 terminals, with the middle one connected to the gate, which is the polysilicon layer. Here's where the magic happens. When an electrical charge is applied solely to the outer terminal, electricity cannot flow, and the transistor remains blocked. However, when a charge is also applied to the middle terminal, electrons from the P layer are drawn towards it, accumulating at the border between the silicon crystal and the insulating gate oxide. This accumulation creates a channel beneath the gate, between the islands of N-conductive material, allowing electrons to flow. In essence, this enables the transistor to switch back and forth between being on and off, or 0 and 1 in the world of binary code. This switching action is at the heart of how microchips process information. Now, let's talk about how these layers come to life on a silicone wafer. The chip manufacturing process begins with a meticulous design phase, involving complex layouts, simulations, and functionality testing. Special design tools are used to create detailed plans and 3-dimensional blueprints of the chip's sandwich-like layers. These blueprints are then transferred to photomasks, which serve as templates during the chip fabrication process. The fabrication process must occur in a dust-free environment with stable temperature and humidity levels, which is why it takes place in a clean room. Clean rooms are ultra-controlled environments where even a speck of dust larger than 0.5 micrometers is not allowed in around 10 liters of air. To maintain such cleanliness, clean rooms have sophisticated ventilation, filtration, and supply systems. Employees working in these areas must adhere to strict dress codes, refraining from wearing makeup or jewelry and avoiding smoking before work. Access to cleanroom production areas is granted only through special airlocks. Depending on the size, one wafer can hold many chips. The process starts by heating the wafer to around 1000 degrees Celsius in a furnace, creating a non-conductive layer. Next, a light-sensitive material is spread evenly on this layer, and then the wafer is exposed to light using specialized machines. The light exposes the circuit patterns on the wafer. After exposure, the exposed areas are developed, revealing the underlying oxide layer. Unexposed areas remain protected. Following this, the exposed oxide layer is selectively removed using either wet or plasma etching. In plasma etching, special gases react to remove microscopic layers, precisely creating the desired patterns. Once the photoresistant material is stripped and the wafer is clean, it undergoes further oxidation. Then, a layer of electrically conductive polysilicon is deposited. The process of applying polyresistance, exposure, and stripping is repeated, ensuring only specific areas remain intact. Next comes the doping process, where impurity atoms are introduced into the exposed silicone, slightly altering its conductivity. Another oxide layer is applied, and the wafer goes through another photoresistant cycle. This creates contact holes that allows access to the conductive layers, enabling the integration of contacts and interconnections. Metal alloys are deposited onto the wafer, and the photoresistant and masks are applied once more. After an etching process to create a smooth finish, the microscopic structures are polished away with precision. This series of steps may be repeated multiple times depending on the chip's complexity, until the integrated circuit is complete. The result is the tiny microchips that power our modern devices. The final stage in the chip's fabrication process is assembly. Here, the individual chips are placed into packages and terminals are attached. The end result is a finished semiconductor device ready to be mounted on circuit boards. These devices can feature different types of terminals, with over 1,000 connection contacts possible. Some examples of packaged semiconductor components include specialized larger packages used to power semiconductors. These power semiconductors are designed for applications such as trains, electric cars, solar panels, and wind turbines, where they must handle electrical currents of up to several hundred amps and voltages running into the thousands. To dissipate the heat generated by switching at these levels, cooling areas are integrated into these packages. Throughout the manufacturing process, cutting-edge technologies and rigorous testing are employed to ensure the highest quality standards of chip yield. Researchers and developers use scanning electron microscopes to repeatedly check chips at various points in the production process. These semiconductor components, despite their tiny size, have a significant impact on our lives today and in the future. As demand continues to rise for innovative semiconductor solutions that make technology more efficient, safer, and environmentally friendly, the precision and quality at every stage of production are essential in delivering these building blocks of modern technology. And there you have it, the fascinating journey of how microchips, the unassuming powerhouses, come to life. From the meticulous manufacturing process to the careful assembly, these tiny wonders drive the technology that shapes our world. The relentless pursuit of innovation in the semiconductor industry continues to bring us closer to a future where technology achieves more, consumes less, and is accessible to everyone. So, the next time you pick up your smartphone, use your laptop, or interact with any electronic devices, take a moment to appreciate the incredible journey these chips have undertaken and the countless possibilities they unlock. Thank you for joining us on this insightful journey through the world of microchip manufacturing. If you found this video informative, don't forget to like, share, and subscribe to stay connected with the latest advancements in technology. Until next time, stay curious and keep exploring the amazing world of science and technology.